Hello and welcome back to another video. D3D12Ez here on the Lytic Fuzzle channel. In the last video we managed to finally finish our pipeline state and to bind it, and everything seems to be good, but we do not get an output. Why do we not get an output? Well, because we are still requiring some runtime bindings, calling it out Viewport and Scissor rectangle, or better to say, the Rasterizer. Right, the input assembler is configured, however the Rasterizer is not. Let's talk about it, why the Rasterizer does need configuration. Well, the Rasterizer needs configuration because it doesn't know anything about our window. It's not bound to it. The Rasterizer just has a render target, but it doesn't know how to access it, how to access properly it, how we want to access it. It doesn't know that. The Rasterizer is just there to rasterize from normalized device coordinates that we specified above here with our triangle to rasterize from that to a certain pixel value. But we need to tell the Rasterizer the range where we want to raster into. And that's what we need to do at runtime, right? Because this is kind of like runtime dependent on how big the window is. And if the window resizes, the Rasterizer bindings need to resize as well. But the PSO and the root signature stays the same. So it's bound via the command list. Same goes for the input assembler. Vertex buffer can change, primitive topology can't really change, but it is still dependent on how the pipeline works. You can have a pipeline that can process both like points and triangles and stuff like that, so it's set at runtime. Now, how do I set the Rasterizer? Command list, RS for Rasterizer, and you can see that we have actually 4 options here. Shading rate is something advanced. What we care about is, first of all, the viewport. We want to bind a viewport. Now we can bind multiple viewports. We're just going to bind one to a D3D12 viewport, D3D12 viewport VP. There we have our nicely friendly viewport, and it's bound. Of course, the viewport needs description. The viewport actually binds to a window, so it has a top left X, a top left Y, a width, height, and a bit of depth values that are also used for something. Top left X and top left Y, they shall be both at 0. That's simple. Alright, then we need to specify the width, and we need to specify the height, and the whole world is burning, because we don't have access to the width and the height. The window is currently not exposing it, so let's fix that. Let's go into window.h, and you can see we have width and height as uint in here, but it's not exposed via a function. So inline, uint, get width, and we can return the width. Same goes for the height. Yeah, let's rewrite it. It doesn't really matter. Get height, and what we need to do is we need to return the height, and everything is good. Width and height returned properly. Now we have a way. Okay, interesting why you are burning currently. It's probably just an issue. Now we have a way to get width and the height from the window, and now we can use it in the main to get it. So dx window get width, and the same goes for height. And now the only thing that is missing are our min and max depth. And now, again, if you're not on a tutorial, you need to do a whole research on how depth buffering and depth stenciling works, so that you know how min depth and max depth work. But I told you, we're gonna do it step by step ad hoc. So I'm gonna, yet again, specify you some certain values that you just need to believe me that they are correct. Min depth is gonna be 1.f, and our max depth 0.f. Floating point values, minimum is 1, maximum is 0. Looks ugly, looks not good, but is correct, actually. So there we go. Now I pasted somewhere something that I didn't want to paste. Okay, there we go. Now we are ready to press F5 and see if everything works. But let's see if we are getting something. And as you can see, we see nothing. Why do we see nothing? Because of something called a scissor rectangle that's by default spanning from 0, 0 to 0.0. DirectX 12 has, next to the viewport that indicates how to draw on that window, something called a scissor rectangle. The scissor rectangle allows you to just draw a portion of the window without rescaling the viewport. The viewport kind of like scales off the window, and the scissor rectangle cuts out a certain area that's valid for drawing. Now by default, the scissor rectangle is spanning from 0 up here, top left, to 0, also top left. And everything that's inside of the scissor rectangle is outputted by the rasterizer. So everything is working. We are currently, or should currently already invoke our vertex shader, and our rasterizer should already be fed with vertices. Better to say a triangle, but it is going to rasterize this triangle, and then it's going to see that the scissor rectangle is spanning from 0 to 0, and that the triangle is not in that 0 to 0 range, obviously, or no pixel of the triangle is in the 0 to 0 range. It's doing that on a per pixel base. And yeah, therefore we see nothing. How can we fix that? We need to set our own custom scissor rectangle. And that's why people hate DirectX 12 and they love DirectX 11. So screct for our scissor rectangle, and I'm going to specify a left equals top equals 0. So the top left is now still specified. However, now I'm going to specify right to the width of my window, which is basically already spanning the scissor rectangle from the top left to the right top of our screen. And if I now specify bottom to the height, now we have a scissor rectangle that's spanning the whole screen, which we of course need to set. rs set scissor rects. I want to set one rectangle to the screct in here, and now the rectangle is placed on the GPU. And if we're now pressing F5, we finally see our white triangle. It did take ages, but there it is. A nice big ass white triangle. Now, that's not very nice. Let's play around with it. Let's play a bit around to get a bit of an understanding how stuff works. First of all, I want to again show you how the viewport and the scissor rectangle work, because they are kind of like abstract concepts, and when I started DirectX 12, I just got the meta information. They need to be width and height as a window, and that's it. And I really didn't understand how they worked. I just know that they need to be as that. But you can find out how they work by just playing around with these, right? Let's just take a half of the width for the viewport. What happens if I take half of the width and half of the height in the viewport? Well, we are getting a triangle that's just spanning the top left quad of our screen, because our viewport is now spanning that area of the window. But the rasterizer is still scaling our whole triangle in that area. And the output measure is still going to take these coordinates and merge them correctly on our buffer. And so we have only 1/4 of the screen used. Could also offset them, right? Let's maybe offset them by 500. Offset them by 500. Top X and top Y. The triangle has moved down a bit on 500 by 500. Of course, that's not how you want to move a triangle, right? But it's giving you a bit of an idea how this works. How would you use a viewport? Well, if you have something like split screen rendering, if you have like local multiplayer on one keyboard and you use split screen rendering, you once draw to the left half of the screen and once to the right half of the screen with different cameras and different renderers set up. And boom, you have a split screen game. That's the idea. Now let's revert it back so that we are back at normal, and then let's play a bit around with the scissor rectangle. So now back at normal, or should be back at normal. Let's see. There we go, back at normal. Let's play around with the scissor rectangle. Well, scissor rectangle, similar. We're gonna just divide it by half, so we're only gonna spin it half of the screen. Now on the viewport, we saw the whole triangle on the top left. What if we are doing it with a scissor rectangle? Well, as I told you, it's going to cut away everything that's not inside that rectangle, so you can see only 1/4 of the screen is filled, but not with the whole triangle, with that part of the triangle that would be there if the whole screen would be filled. And this basically means the viewport is over the whole screen, so it would render on the whole screen. However, the scissor rectangle is cropping away everything that's not inside of it, so you can see the triangle is there. What you can do is you can of course also play around. Let's maybe now take 200 as a value, move it 200 to the right and 200 down. And if I do it like that, boom, you can see we have a different area of the triangle covered. And that's the whole magic. There's no magic behind it actually. It is plain as simple. It's simple to use. Simple triangle, simple vertex, simple rectangle, simple viewport. It is not complicated. However, we're gonna get complicated now, of course. So what I want to do is I want to play a bit around with the blending here. You can see that we have blending disabled. What happens if I enable blending? Well, as you can see, source and destination is 0. So what I would suspect is I would suspect that I see nothing. Oh, and I actually see something, and it's not nothing. Why is it not nothing? Okay, that's interesting. Okay, yeah, actually, I can tell you why we are seeing something. Well, have I reverted my changes down here? With the scissor rectangle? No, I have not. It's still at 200. This is why it was looking a bit too ugly. What you can see now is you can see that our triangle has turned black. Right? Why has our triangle turned black? Well, I can tell you why it has turned black. It has turned black because we have taken a white pixel and a blue background pixel. We have both multiplied them by 0, so the white pixel and the blue pixel, they are both now black pixels, and these two black pixels have been taken together and added together, which is still 0, and then merged out of it, so now the triangle has become black. If I would remove that mask and set the mask to 0, basically don't write at all, well, you can see, since now we are no longer writing, it is no longer black. Okay, that's the idea. But that's not, of course, a good idea for using blending. Let's now play a bit around with these. Let's play around with the destination blend and set the destination blend to 1. What is if we are adding the destination blend to 1? And we enable blending. It is, of course, blue, because now what we have done is we have taken a white pixel, multiplied it by 0, which is 0. We have taken a blue pixel, multiplied by 1, which is blue. 0 plus blue is blue. So we are blue. Blue, double D, double die. No, that's not what I wanted to say. All right, so let's invert these. Let's say the source is 1 and the blend is 0. The destination is 0, which means blue pixel times 0 is 0. Or black. We are already doing math with colors. So kind of like blue times 0 is black, plus white times 1, which is white, black plus white. In terms of color value, 0 plus 255 is 255, which is white. And now I would suspect that I get a white triangle on the screen. And there it is, a white triangle back on the screen. I can also try to play around with these right masks, which I wouldn't recommend because it looks a bit odd. But if I would just enable depth writing for the red color channel, you can see that we are getting that. It is not looking red because we are only writing to the red color channel. So the blue value, the blue component is still in here. We have just updated the red component of the blue color that was already on the screen. Everything else was not updated, so it was still the old color value. And you can see we're getting interesting effects like that, even though we would suspect a complete red triangle, which is of course not the case, because it's only writing to the red channel. The other channels that were blue are not modified. Now let's play a bit around and merge them together. What we can do is we can set source and destination blend to 1 and add them together. If we do that, it's actually going to still be white because we are overshooting. But we could try and simulate it by going into our pixel shader and remove a bit of attenuation from that color. So I can actually remove attenuation by doing it a bit different. Let's actually now compose them out of a float. Let's compose the color out of a float 4, which comes from a float 3, and then add it like that. So we have a float 3 and with that, and then we can add a bit of an attenuation here, times 0.2, so that we are not as white as expected. Now you can see that we have a white triangle overlaid over our background color. A gray triangle, actually. Maybe I should put destination blend to 0 again so that you can see how this works. If I put that to 0, you're gonna see that we have kind of like a gray triangle in here. And if we are taking like this gray triangle and we want to overlay it with the background color, we can use blending in here by providing 1. And if you take a look at this, you can see that we kind of like get our attenuated triangle blended over the background color, which you already saw previously. So blending works. Right? Let's maybe do logical blending, because logical blending might be also interesting, even though I don't think that it's gonna look interesting. If I do logical blending now, we should get our old color that we have, because we have currently no op in here, and no, okay. We can't do logical blending. Logical op and blend enable cannot be both set to true. Okay, so we need to set the other one to false. So if we are using logical blending, then we can't use normal blending. Yeah, makes sense. So let's put this to false. Let's see what we got. No op should mean no operation. The render target format at slot 0. Okay. We can't try out logical blending because our render target doesn't support logical blending. So yeah, sorry for that. I wanted to try that out, but it doesn't work, right? Because it's the wrong format. We would be required to use a uint format, an unsigned integer. Unsigned integers are kind of like values that are not color values. So these ones would allow us to do blending on, but this is like a color value. Even through it's still like unsigned integers, but the format itself doesn't support it. You can see pixel shader output SV target 0 has type that is not unsigned int, where the corresponding output measure render target slot has logic op enabled. This happens to be well defined. The raw bit output from the shader will be simply interpreted as uint bits, and the blender output will fill out whatever. The warning bleep blah bloop. It's telling us stuff, but it's an error. It doesn't work, right? So that's not what we want to do. Okay, so we have now a bit of blending in here. However, what I now want to do is actually now want to not keep the source blend at 1, and I want to put the attenuation back to 1. So now I want to have full attenuation, but I want to still blend together. How can I do that? Well, I can do that by actually scaling my input color a bit. So if I want to have full range or full attenuation in my shader and want to blend it with an existing color with maybe a attenuation of 0.5, but the attenuation shall not be calculated in the shader like I have done that, then we can also specify a blend factor. So instead of blend 1, I want to have my blend factor as attenuation. And if I use the blend factor, it's going to use that. It's probably going to be 0 by default, the blend factor, or it's going to give me an error. No, it's actually by default at 1, so I can see a white triangle. However, we can actually modify the blend factor by controlling the output merger. So EARS, and now we are going to the output merger. And this blend factor that I've just specified is inside the runtime bindable output merger stuff. So OM set blend factor. There are actually 4 blend factors for the 4 color channels. So I did the float array, BF for the blend factor, and I am just going to provide 0.5, 0.5, 0.5, 1.5 float. Of course, I forgot the floats everywhere. And if I do it like that, then I can provide my blend factor in here, and if I start it, you're gonna see that our triangle should have got a bit of a blend factor, which I can't currently see actually. Why can I not see it? It should have multiplied these. Is it too less? Let's do a bit lower attenuation. Maybe also move that one, but this shouldn't change it. Okay, there you go. The attenuation of the blend factor was just too high. So I can see if I put 0.1 in here, the attenuation is good. Now, why is something like that useful? Well, because this allows us to actually change the blend factor dynamically at runtime, right? This is now going to be totally ugly. Static, float, BFF, FF, and the blend factor is by default starting at 0, and then I basically do BFF plus equal 0.01f, and if BFFF is bigger than 1f, then I'm gonna set BFFF equals to 0.f, and like that. Okay, and then I can take my BFFF and I can plug my BFFF just inside of that array. And now we have a very ugly sweeping through the blending factors that are available. So what you can see now is you can see that our blending of the triangle works, and this works by runtime. We have programmed our first animation with a blend factor and the output merger, and just modifying output merger states. But this is what you do, right? You need to know how all of these pipelines work together. You need to get hands on these things, because DirectX is dry, it is complicated, so we need to have hands on, like that. That is fun, right? A blinking triangle, that's fun. Let's make this blinking triangle a bit colorful. How can we make it colorful? Well, we could, in our pixel shader, just define a static color, like a float CF, our color factor. Oh no, let's directly write them in here. No, come on. No. Float 3 color equals. And I think we should be maybe even able to just do it C++y, construct my color like a constructor, maybe? Let's see if HLSL allows that. I don't know why it shouldn't. It's like a, why is it a C compiler? I don't know. I still don't know really if it's a, I think Clang is like, let's do it as they intended it to do. Let's create a flow 3. Can I do auto? Doesn't seem like it. I know which feature set this is using. And then let's take the color, and then we have my blend factor in here that's now factored out, and then I can add the alpha value of 1. So let's make a red triangle, so red component to 1, all of them to 0, and there we go, swiping through a red triangle that's still blended. That's why it's not getting completely red. That's interesting. I would have expected it to get completely red. But since we are using adding... No, it's not getting completely red because we are still having the other color components of the blue background. It's getting 100% red component, but it's not looking completely red. Sometimes it's a bit hard to understand these things if you are even teaching them. But yeah, we can add color in here, of course. That's like the whole idea, right? But this color is still too static. Let's now move to the next stage. Let's remove all that blending shit. We don't need that. We also don't want to have blending. I'm gonna keep that 1, but I'm gonna add blending 1 to that, and then I'm gonna add 0 in here, so that we are blending but without doing stuff. And now we basically should have a completely red triangle. Basically, yeah, there we go. And now I want to swap colors of the triangle. How can I swap colors of the triangle? Well, the output merger is not sufficient. I need to runtime inject data into my shader. How do I do that? With a root constant. Root signature, we talked about these. Specifying root signatures in HLSL. I always use these references because I don't really remember these. And what we want to specify is a root constant, and the root constant shall specify the color value that we want to put onto the GPU. So I gotta go to my root signature, and I'm gonna add another parameter to the root signature. And since it's a comment, we do it like that. And what we specify is a root constant with 3 values at the buffer slot 0. And this basically means we have 3 32-bit values at buffer slot 0. How do I want to document them? Well, I want to document them above here, root signature layout, and we're going to have 2 layouts, root signature layout CPU, and we're going to have a root signature layout GPU. Now the root signature layout CPU is quite simple. At the slot 0 we have a float 3, which is the color that we want to specify. And on the GPU side, it's a bit different, a bit harder to specify. It is at the slot B0, and that's a register, and we have a color, or a float 3 color. And now I have basically specified my layout, and now I just need to use and provide my layout somewhere. How do I now add them? First of all, I want to add them onto the shader. Now this is actually quite simple. Float 3 color. And we're gonna say this is at register B0, and now we basically remove that line down here, and now the color is bind to the root signature. If I would now run this should already work. And you can see that we have a black triangle because there's no data in the color channel currently. So we have a black triangle. Now, of course, we want to specify these colors. How do I specify them? Well, in my main, of course, because this is now runtime bound again to the root signature. So we have bound the PSO, and now we have root arguments that we need to specify. So command list has functions, set, graphics, root constant buffer view, descriptor table, shader recess view, root signature, unordered access view. In this case, we want to set a root 32-bit constant. And you can see that this one takes a source data and destination offset, so this doesn't work. We have multiple of them. Set constants, multiple of these. Root index, well, this is now the layout. You can see in my root signature, the layout on the CPU side is 0 for the color. So the root parameter index is 0. Now we need to specify how many values we want to set. We want to set 3, and then we need to provide a few parameters. And if I would peek in here, I would suspect that we have, yeah, there you can see we have the destination pointer here, which is a UN pointer, and then we have a destination offset in 32-bit values. So source data and destination offset. So we are starting here, the number of values that we are setting, and then we have an offset. Because you can actually set them independently. We want to set 3. We need the data, and then we need the number of values, or better say the offset. Now, where is the color going to come from? Again, a float array color. I'm going to now call it color as well. And the float array color, I'm just going to provide a red color currently. We're gonna use sweeping there as well in a sec. We can also try a bit of color puke, but I don't know if I can get this up running fast. So you can see, there we go. Now we have binded in here. Let's see if it works. If we are getting a red color on the screen, which we might not get, but we are getting it. Sometimes they have a bit of a problem if they are not aligned correctly. So what I would never recommend you is just setting 3 values. 4 would be better, even if you're packing and unpacking them. But they need to be kind of like in order. But this is actually fine. So you can see, there you go, red color triangle. Set it at runtime from the CPU. Can we do color puke? Okay, let's try out if we can do color puke. I don't know really if I can do color puke. Can I do color puke? How could I do a bit of color puking? I think I have an idea on how I could do it. How I could do color puking. Okay, so we're going to start with a black triangle. And color puking will go in its own function. I mean, this is not totally useless that I do color puking. So how do I do color puking? So first of all, I need a bit of a puke state. Okay, this is now completely ugly. Puke state is going to be 0 by default. And then what I'm going to do is I'm going to do color at puke state plus equal 0.01 if color at puke state equals or not equals bigger than f, then I want to go to the next color channel. So that's not really gonna work. But again, okay, this is okay. We're gonna do it differently. Puke state plus plus is what we're gonna do. And now if puke state equals 4, so if we are sweep through everything, then I'm gonna set color to 0. This is not a good color puke, this is a bad color puke, but I can't come up with one that's better inside of that video here, so sorry for that. So it's going to be set to 0, and actually what I need to do is I check for 3, because we are 0-based indexing. Yeah, so now we have a bit of color puking. It's probably going to look a bit ugly, but it's going to be sufficient to show you that it works. And again, these are like all now defined on frame rate. If your frame rate is faster, this color puke is going to be faster. So yeah, so let's puke colors around. Let's see how it looks. There we go. It's gonna get red, and then we're gonna. No, it's not looking too bad actually. I mean, we could have a bit better color puking, but I think it's actually fine here for this purpose. So there we go. We have dynamic color puking. Nice, or not, depending on how you see it. But I think it's quite fun. It's complicated because we have done a few things, including like root signatures, but I like it. I like the idea of it. It's actually not too hard, and it's nice. Thank you for watching. See you in the next video where we're gonna get to textures. Not in the next, but the next few. We're gonna put in some textures and actual better data than just color puking on a triangle. Thank you for watching. See you in the next video. Make sure to like and subscribe, and have a real nice day. Bye!